My name is Tracie Sempier. Welcome to Storm Tech, the tools behind the forecast. We're really glad that you could join us today. It's interesting that we're in the middle of Tropical Storm Bertha here on the coast where I'm located. So I'm at the Gulf Coast Research Lab. I don't think it's nearly as bad as what was predicted, but I still appreciate folks being able to move onto an all virtual platform because many times when we have these tropical storms come in, our road gets flooded down there, and we were planning on using one of our classrooms here. So thank you for being flexible and being willing to jump on Zoom for the meeting this morning. I do have some help. I have Christiana Allen. She's my colleague, and also you'll see several of the resources that she's prepared throughout this presentation. Christiana is actually up at Jackson State, so we're in two very different locations. There she is. So we're going to be the ones that are going to be facilitating the meeting today. And so if you have any questions, if you'll please let Christiana know in that chat box, especially if you're having any technical difficulties. Christiana, did you have anything you wanted to add before we get started?
No, I think you covered everything. Looking forward to the presentation.
Awesome. Thank you. So I just wanted to get a real quick idea of who all we have today. If you could do us a favor and just place your name and your organization in the chat box. Just let us know maybe why this topic is of interest to you. This is the first time that we've offered Storm Tech as a condensed webinar. We typically have each one of the topics that we're going to cover today in a full-length webinar, and we typically have guest speakers. And so we're going to give you access to those webinars in case you want to do a deep dive on any of what we cover today. So I'll give everybody just a second to find your chat box and just let us know who all is here today. So I'm not seeing anything coming through in the chat box, which is making me feel like it might be, oh no, it's not disabled. Okay, great. um, okay, so we've got folks here with us from Alabama, so welcome. Over at ADECA, that's great. We're glad that you're here. Oh, welcome, Stephen. Also, Stephen Deal. We have you from our Mississippi Alabama Sea Grant program, so welcome, Stephen. Someone from up in, I guess, are you up in Tuscaloosa, Xavier, at UA's campus up there? Okay, great. Welcome. All right, welcome to Casey. Great. So we've got a variety of folks, and it looks like most of you may have wanted to participate virtually anyway. So this worked out really good. Okay. Well, I just want to get started now that we've got everybody. We kind of know who's online. I am interested to know, and you feel free to share this in the chat box as we go along, your thoughts on things. But this course was really intended to give a really broad overview of many of the technologies that are used to do in the forecasting. So all of which are being used right now for Tropical Storm Bertha. And also, to let you know, we're going to go through these different ones pretty quickly, but then at the end of each one of these technologies, we're going to give you some resources that Christiana is going to be placing in the chat box. If you miss those resources that are in the chat box, don't worry about it. We will send a follow-up email with links to all of these, the extension publications, the webinars that go in more depth. So just know that you'll have a wealth of resources, and that way, if you ever want to go back and watch maybe a more in-depth for one of the particular technologies, you're welcome to do that. So before we get into the different storm technologies, I wanted to give you a little bit of a background about sort of what Christiana and I are here doing and sort of what our role is. We are both extension specialists. We work for the Mississippi Alabama Sea Grant Consortium. And as I mentioned earlier, we're located in different places. I'm down on the coast in Ocean Springs. Christiana's up at Jackson State in the middle of the state. And our job is to take the science that's produced by the National Severe Storms Lab, Vortex Southeast, and now Vortex USA program, and translate that information for non-technical audiences. So we've had this partnership since about I guess the year 2000 is when it started during COVID. Vortex has been around a lot longer than that, though. The actual research program has been around since 2015. And so it's our job to take anything that's new that's coming out of that program and make it and figure out what are some practical risk communication messages that we can communicate during on the ground events. That might be a tabling event, it might be a training that we do at a library, but it's all focused around severe weather. And so that's just a little bit about our program, just so you know kind of where Christian and I are coming from. We're the outreach arm for that program. And I wanted to just summarize in this slide really why it's so important and why the Severe Storms Lab decided to focus on the Southeast. And I love this paper by Walker Ashley. We are using this with permission, but it really outlines the 4 big reasons why folks that are in our area are so much more at risk for severe weather events. So if you look at that top left, you'll notice that there are some shaded areas, and in those shaded areas, there are some numbers, and those numbers are equating to the percentages of fatalities during nocturnal tornadoes, so nighttime tornadoes. So more than half of the tornadoes that we receive in the Southeast area do happen at night, and that's a problem because we know that sometimes people need to actually have proof of seeing the storm on ground before they will take cover, and so we can't do that at night because we can't get those photographs. We also have a lot of rain-wrapped tornadoes in our area. Again, that makes it very difficult for people to see visual proof to take action. And so having that many nocturnal tornadoes, and you'll see there are other numbers kind of around us, but in the Southeast, all those numbers are pretty high. Then if you move over to the right, the top right, you'll see that that's showing you we have a high percentage of mobile homes by county. That's an issue because of just being in an unsafe structure during a tornadic event puts you at higher risk. And so that means that when Christian and I do our outreach, we really focus on what are some other options for safe sheltering, especially if you're living in a mobile manufactured home. We also talk about leaving earlier than and not really just waiting for that tornado warning to come in, really leaving at the watch and making sure you know where to go. Then if you go to the bottom, you'll see the bottom left there is a high percentage of forest cover. And this is extremely important, especially when we get into talking about the Doppler radar and some of the storm tech tools, because with that kind of forest cover, it does make it difficult, a little more difficult to get accurate readings. And then if you look on the bottom right, the high percentage of poverty by county, this is important just from a social vulnerability aspect, and knowing that it's going to take people longer to recover if they already don't are living at that poverty line. We also know that from surveys that we've done that those folks tend to not seek medical care because they don't have insurance. So there's a whole host of social vulnerabilities that we have to look at. So in our area, I like this diagram because I feel like it puts so many of those things all together in one place that we have to be concerned about. Okay, so the first section of what we're going to talk about today is just how forecasters build the forecast and really, you know, what tools they have available to them to do that. And so as we're going through, I just wanted to say that, you know, I think a lot of this is probably an overview for those of you that are on today. I'm sure that you're aware that these things occur, but I think this is a good place to start. We have a lot of different weather data that's being collected. So the weather station, like that's what a picture that you see there on the right, this is a weather station that's set up actually at an airport. We know that we have these in several locations, and we know that many folks actually just have even smaller personal weather stations at their home. We have satellites, we have weather radar, which we're going to talk about today. And, you know, all of these things are important because having more accurate data and getting that data in a timely manner really helps meteorologists make a more reliable forecast. And that helps when they're issuing early warnings for severe weather. Now, we also have weather data collected by weather balloons, which I will show a picture of today, ships and buoys, which are, out over the oceans and seas, and then aircraft. So you see a weather balloon down there in the picture on the left, and these are being released typically at the National Weather Service offices locally. And then on the right, a picture of one of the planes that flies and to gather this information. In fact, I guess it was just in May, we had the hurricane hunters here in Mobile, which was exciting. They have so much instrumentation on board their planes. I had not ever taken a tour before. I would suggest if you get a chance to do that when they're touring, it was really eye-opening just how many of the types of storm tech that I'm going to show you today, but they have little miniature versions that they have as they fly through the hurricanes. Very, very cool. So we're going to start with Doppler radar. And just to kind of give you a brief overview of what this is a specialized weather radar. It detects rain, snow, hail, and storms. It also measures the speed and direction of moving precipitation. There's a picture there of a tower on the right of what a Doppler radar could look like. And sometimes they look a little different. I'm going to show you some other pictures of these in a moment. But I like to show the schematic at the bottom because I think that we're used to seeing the radar look a little bit more like this with the antenna and the positioner. Well, that is inside that dome. And I get asked that question quite a lot. So it uses the Doppler effect, which is the change in frequency of radio waves that are bouncing off objects and then reflecting back to the radar. And this is a good illustration of what that looks like. The radar sends out radio waves. Basically, the raindrops or snowflakes or whatever precipitation it is in the air is reflecting those waves back. And then the radar is analyzing those returned signals to figure out, where is it? How much is there? What's the speed of movement? And in many cases, what is the rotation? If there's a rotation there, then we know about, it gives us more information about potential tornadic formation. So on the left-hand side, you'll see this is just a static diagram, of course, on the left, but it shows the radar emitting the outgoing radio wave, and then it bouncing off the raindrop and coming in, the returning wavelength. Now, this is a singular polarization. We now have moved in Doppler radar in the early 2000s to dual polarization, and I'll talk about that in just a moment. So why is Doppler radar important? Well, it tracks thunderstorms and heavy rainfall. It was definitely used to help track Tropical Storm Bertha that we have out in the Gulf right now. It detects rotating storms, which you'll see a picture of on the right, and it does monitor other precipitation like snow and hail. Again, this is used for early warnings and severe weather, and it does help us improve the accuracy of our forecast. So if you look there on the right, this is something that you probably see quite often, especially if there's a tornado on the ground, is this hook echo. So this would be a picture of what that radar would come through, and what you're seeing is that rain wrapping around and starting to rotate. That gives meteorologists an opportunity to say, well, that's probably where a tornado could form. But in this instance, one of the things that we'll talk about in a few minutes is they might get that hook echo, but they also have to ground truth that, and they use storm spotters to do that. So we'll learn a little bit about that in just a moment. So the nice thing about radar is that it has continued to be developed over time, and there's been lots of technological improvements since the very first installation of Doppler radar. We now refer to sort of a network of systems called the Next Generation Weather Radar, or NEXRAD. So if you hear someone talking about NEXRAD, this is a network of several Doppler stations located throughout the country, and I'm going to show you a map of where those are located. And essentially, these are operated jointly by the National Weather Forecasting Offices and the Federal Aviation Administration. And sometimes those groups are co-located together, as you know, usually at airports. So NEXRAD was basically, they took Doppler radar, and then in the early 90s, they started to install these larger NEXRAD units across the country. And these do have, and then they were updated again in the early 2000s with dual polarization polarization technology, which essentially means that picture that I showed you before where they're shooting out transmitting the radio waves horizontally. They now, with dual polarization, do horizontally and vertically. And that really improves the amount of information that we're able to get. So now it kind of took the radar from 2D to 3D with dual polarization. And that was in 2011 was the first time that we actually had access to dual polarization. Now, why is that important? Well, because now we know what kind of precipitation and how much like rain is accumulating, and we can detect and track the debris of tornadoes. So sometimes that debris marker is picked up with the dual polarization, whereas it wasn't before, and that helps us to give us more confidence that there's a tornado on the ground. So this is just what the NextRad system looks like. Again, it emits pulses of electromagnetic waves at each one of those sites, again, housed in those big domes, and it can, again, detect precipitation. It can measure wind velocities, and these are the stations that we currently have around the United States. I believe the first one was actually installed in Virginia, and then they kind of just kept moving across the country, and we now have 160 sites. Now, as wonderful as our Doppler radar is, and you even have access to the radar results right on your phone when you're monitoring the weather, but there are some limitations. And I think this is important to point out because the reason we have other storm technologies that we're going to talk about together this morning is because not any one technology is helping us to see the full weather picture. So one of the biggest things with Doppler radar is based upon the location of that radar. So you'll see in the picture, that far left corner, that's where the radar station is. Let's say the Earth's curvature, the radar beams, then they travel in a straight line, but the Earth curves away. So that makes the beam go a little bit higher the further away it is from the radar. And so it can overshoot storms, especially shallow storms. And I've got a couple of pictures of this throughout just so you can get an idea. So you might do a really good job of forecasting what's going to happen there in city A, but maybe a less great job of forecasting what's going to happen in city B just based upon that curvature. Also, the radar can't see things just directly above the station. So wherever that radar is, it can't see what's happening right above it because the antenna doesn't point that way. We also have some issues with something called beam spreading, which is where the beam gets wider the further it travels out. And you can kind of see that in this illustration as well. And so the further that it spreads out, that reduces, the accuracy of the information that we're getting back. So these are a couple of limitations for Doppler. There's also some physical limitations to Doppler, and I'm going to get to those in a second. But I wanted to show you this picture really quickly, but because of that curvature and because we don't have radars in every single spot, right? We only have limits to how many radars we have positioned. We do have something else. These are my own personal pictures, so I'm sorry if they're not the best, but this is a Mesonet truck. And in late May, I was able to travel up to the National Weather Center, and they did an unveiling for two large new Mesonet trucks that they're going to have out in the field. See that little dome that they can raise up and down on that beam in the first picture? And then what I was trying to get a photograph of, but I've got a couple of folks in my way, is up inside that dome is where the radar sits. So again, it looks very similar to the other Doppler radars I was showing you, but this one is nice because they can take it on the road, and you do not even have to have a commercial driver's license to be able to drive one of these, which I thought was really interesting. But a Mesonet is basically an automatic network of weather stations, and they are designed to monitor very localized weather or mesoscale atmospheric phenomenon, such as thunderstorms and gusts, things that may not be caught by the other the Doppler radars. And so they can go and place these mesonets out into the field when they know that they're expecting severe weather to happen in a certain place. And so these kinds of trucks and these mesonets can fill those big gaps that I was showing you in the picture that's left by just a traditional Doppler radar. And again, because we know that the storms are coming far enough ahead of time, they can place these in the field in strategic locations. So just one more picture, because I do want to show, kind of bring home why we have to have all these different storm technologies. There are some environmental and physical blockers to Doppler radar. One is ground cover and clutter. So hills, tall buildings, trees, all of that can block the radar signal or provide essentially false echoes. And so this is especially important in the Southeast. We have a lot of rolling hills. We have a lot of little, even when there are places that are not mountains, we still have that dense forest cover and rolling hills. And so that does make it difficult for radar to signal correctly. And then again, we talked about some beam bending before, but there also changes in air temperature and moisture can cause that beam building or the refraction on the radar. And again, can cause false readings. And then that line of sight, it only measures the motion directly towards or away from the radar site. It misses any sideways motion and anything that's perpendicular to that beam. So I like this diagram as well, just because it shows just how large that gap can be when the radar is working. And so in this particular diagram, I think that's a little over 3 miles of a gap, the further that the radar is away from the actual storm. So that's just a brief overview of what Doppler is, how Doppler has kind of changed over time. But we do have some additional resources that you might want to consider. And so Christiana actually hosted an entire webinar on Doppler radar, and we had 2 meteorologists from the Jackson Weather Forecasting Office there, Latrice Maxey and Eric Carpenter. And so Christiana is going to just place the links for that webinar in the chat box. We've also done an extension publication. So if this is something that you're interested in, or maybe you want to use this at an outreach event, you can just print this off. It's a front and back, so it's just one page, and you can take that with you. But it gives some essential information about Doppler radar. So I just want to pause for just a second and just see if folks have any questions about Doppler before we move on. And you can take yourself off mute if you have a question, or you can type it in the chat box. Okay, well, if you do have a question, then feel free to save that or stick it in the chat box, and as we move on. So moving on from Doppler, I did want to talk just a few minutes about the radiosondes. And this is something that was actually pretty new to me when we first started this. I have always seen weather balloons, but I never really understood what was attached to a weather balloon. And so this is what's attached, or this is one of the things that's attached. And this is a small instrument package, and it's attached to a certain spot on the weather balloon. So I'm going to show you another picture in a second about where this sits on the weather balloon. But this is another way that the National Weather Service can get a good handle on that gap area, on that from the ground up until wherever that radar might be missing. It measures atmospheric conditions as it moves up through the atmosphere. So as the weather balloon carries it up, it's measuring things like temperature, humidity, air pressure, wind speed and direction. And so this particular instrument is limited by how far up the balloon can take it before the balloon pops, right? Before it comes back down. And so this ascends about 19 to 22 miles on average. And so that's a pretty long way when you think about it in terms of gathering that atmospheric data. So it does give us the information that we might need for things that might form on like a squall line, for instance. And it sends that real-time data back by radio to ground stations. And then eventually the balloon bursts and the radiosonde descends. And it usually comes down like, in a little parachute. And I'll show you again a picture of what that looks like. But the Weather Center doesn't go around and collect these. You can either dispose of it or you can keep them. That's up to you, but sometimes people do find these after they've been up. Okay, so this is what it looks like, just the diagram. There's the balloon you'll see right underneath the balloon is the little parachute, and then the person that's holding it in that little blue thing that you see is the radiosonde that's hanging on to that. And then over in the right-hand picture, this is really what it would look like in real life. Those are really huge balloons, in comparison, because they have to go up so far. And radiosondes do help us improve weather forecasting. They do support severe weather prediction. They do provide data for climate research, and they help us with aviation and atmospheric studies. So an important piece of equipment. And the National Weather Service sends these up depending upon how much information they need to gather about an impending storm. So it may be a little bit different depending upon what data they need to collect. So we're going to move on to weather satellites. And then after weather satellites, we'll pause for another time for questions. But with weather satellites, we know that there's two big types of weather satellites, right? So we know we have ones that are geostationary and then ones that are like more polar satellite systems. So we'll talk about those in 1 second. But essentially, they're orbiting the Earth and they're capturing images of clouds and storms. So hopefully, if this animation is working correctly, you're starting to see what's happening in the picture on the right. This is a satellite image from NOAA's Geostationary Operational Environmental Satellite, also known as GOES, GOES. And it is showing the tornadic storm that's forming over Oklahoma. This was back in April of 2023. So these weather satellites are measuring atmospheric conditions, temperature, moisture, cloud cover, and then they're sending that data to ground stations for analysis. And then the meteorologists are using that information to create or help create or enhance their weather forecasts and issue severe weather warnings. So just real quickly, these are the two big types of weather satellites, the geostationary ones, which is the one that I just showed you the data from, the moving picture that you just saw. They remain above the same location on Earth, and then they give us continuous monitoring of the weather systems. But we also have polar orbiting satellites, and they circle the Earth from pole to pole, and they give us more global weather and climate data. So why are these important? Well, of course, they help us track hurricanes, tornadoes, and other types of severe weather. Again, just like the radar, they are helping us to monitor the precipitation, regardless of what form that precipitation's in. And they're helping us observe ocean temperature patterns so that then we can kind of understand what weather might form. Again, they try to help us with early warnings, and they improve the accuracy of the short-term and long-term weather forecast. And just for fun, if you watch the picture on the right, you should notice a difference here, but this is from a weather satellite, and it's not showing you any of those things on the right. It's actually showing you a power outage that occurred. So we sometimes can use the information coming from these weather satellites for other reasons. So if you look there and you watch it long enough, you'll see yep, so it's starting over now, and then in just a second, you'll see it dim. So it captures things like that as well. So before we move on, I just wanted to see if anyone has any questions about weather satellites or radiosondes that I could answer or try to answer. Okay, well, if you do have some, please make sure you stick those in the chat box or feel free to take yourself off of mute. So what I'd like to do now is say, look, and we have many other types of storm tech, but I really want to make sure that in this hour that we have together, we also talk about how some of that technology is being used to make decisions, and then also how members of your community can get involved with some of these technologies. So let's look at how some of this data can be used to make decisions and what that looks like in different places. So I want to take you to a couple of pictures taken at the National Severe Storms Lab, and I want you to see what kinds of things they're doing as the data comes in from all this instrumentation. So if you look at the top right, this is a picture of some emergency managers that are performing tabletop exercises. Note they have the radar coming in on the screens in that room, and they're giving them scenarios to try and work through. Like if you see this, and as it comes in, what kind of messages are you sending out so that they can practice the timing of how they get messages out about severe weather, and they can practice their interpretation skills of what they're seeing, especially because we know that we're all getting our information from the same place, from the National Weather Service, but being able to interpret that and then in a timely manner get the correct messages out, that's really critical for risk communication. And then in the bottom, you'll see this is another laboratory that they have. Again, this is at the National Weather Center in Norman, Oklahoma, where these test beds, we call them test beds, hazardous test beds, exist. And so the bottom picture is showing a picture inside the broadcast meteorologist studio. Again, this is a lab where they can go and in real time be given scenarios, and they can interpret and decide what they're going to put up on the screen for the weather and what messages they're going to put out. This is super important because there's so much information coming in so quickly, and they're not only having to try to analyze that, but they're also having to push out messages to try and keep people safe. And we know that both emergency managers and broadcast meteorologists are very well trusted in their communities, and so we know that a lot of people do get their information in these ways. So this is one way that that data that's coming in from the different technologies is being directly used. They're actually running and performing test scenarios to see what's the best way to get this information out. So here's another thing that happens. There's some physical science, of course, that's going on at the Severe Storms Lab. And I've just picked a few to show you about today because I know that we have limited time together. But FACETS is a program that's now been going on for several years. And FACETS just stands for Forecasting a Continuum, of Environmental Threats. And so from the physical science side at the Severe Storms Lab, they're trying to take what information is coming through from the different storm technologies, and they're trying to make it into a platform that's very usable for broadcast meteorologists and meteorologists. So what you're seeing that's kind of playing out on the right-hand side of your screen, this was sort of a scenario that back in the 2011 storms that hit Tuscaloosa, that's very near and dear to my heart because that's where my family lives. So during that outbreak of tornadoes that just really destroyed a lot of that city, this is kind of the technology that they're hoping to deploy, so that rather than having a polygon drawn, so you see the polygon, the red polygon, right? And that's a really large warning area. But then as that moves away, you'll see just that little beam that really narrows the pathway where they think the tornadic activity is going to occur. And with facets, the idea here is that the computer analyzes this as it's going, and it actually moves the polygon, and it creates polygons of different sizes and then overlays them so that as the broadcast meteorologist is on air, they can actually see exactly where it's anticipated to be going, and they can kind of modify their language as needed. Right now, a broadcast meteorologist, like let's say they have to go off air, they're on for 15 minutes, they go off, there's a commercial. During that commercial time, the broadcast meteorologist is actually having to go in and move their own polygons and pinpoint the movement of the storm based upon the data that's coming in. But facets would take some of that burden away from them and allow them to just have a seamless transition of the information that's coming out. This technology is being tested right now. It's not in every weather forecasting office yet, but hopefully very soon, in the next couple of years, we'll see this used by more and more meteorologists. Another project that's happening at the Severe Storms Lab is called PERILS, and PERILS stands for Propagation, Evolution, and Rotation in Linear Storms. This is a much different project. This is a field project, and so you probably can locate your state there on the map. This is an example of where if they know that there's going to be severe weather in a particular area, they can deploy field instruments ahead of time without putting people in harm's way to try and capture data as the severe weather comes through. So if they know a week in advance that we're supposed to have, or it looks like we're going to have what a storm system is, then they can deploy this instrumentation. So if they're at the top, a mesonet can be deployed. Down there at the bottom, a lightning array instrument can be deployed, and they can put these instruments in place to help them better understand how tornadic activity forms in a squall line. And these types of tornadoes, they're a lot more common in the southeast. They pose a significant challenge to meteorologists and emergency managers because they form so rapidly. But if we have this instrumentation on the ground as the storm is passing through, it increases our ability to collect data to show us if it looks like that tornadic activity is going to occur. Now, on the social science side, there's also some other ways that data is being used to help craft messages and make decisions. So I need to kind of introduce you really quickly because I didn't put a picture up here of this, but in social science, we do have a survey that's now being sent out to our broadcast meteorologists and emergency managers anytime there is to be severe weather in the area. And this is a tool called Tornado Tales. And I'm going to show you a picture of that and give you the website address to it. This is a social science survey where it's asking people questions if they are in the area where the severe weather, especially tornadic activity, is occurring, where they got their information or where they're getting their information, if they sheltered, where they sheltered. It's asking them just a series of questions to better understand people's actions and where they're getting information. So this tool we deployed, I believe it was in early 2022, would have to have been because we have data here from the Kansas storm. So if you look at these are 3 different storms where we've taken surveys using Tornado Tales. So, and they're very different in different states. So we've got an April 2022 storm that happened in Kansas. Those red things are the polygons, and each one of those little dots that you see inside the polygon is actually where a person submitted a survey response. So it's not the tornadoes, it's actually a response to the Tornado Tales survey. And then if you look over at Missouri in the middle, again, there's 2 different polygons that are drawn there, and all those little green dots are people that submitted the social science survey. And then again, in Norman, Oklahoma, you see that polygon that's drawn, and all the blue dots are showing you where we actually have folks that submitted the survey. So 3 totally different events at different times in different states. So kind of keep that in your head because I'm going to show you what then happens with that data. So here is just one little piece of what we gained from those surveys. We looked at warning reception rates across all 3 events, and these are in the same order. The April 29th, 2022, that's the Kansas one. The Missouri one is in the middle, and then the Oklahoma one is on the right. So same order as you saw on the last slide. And notice that the darker color blue is those people that said they received the warning. The lighter color blue are those that said they did not receive a warning. And so this helps us to understand, even during different storms, people's warning receptions rates are different. That does not mean that the National Weather Service did not put out a warning. It just means that for whatever reason, the folks in the survey are answering that they may not have, or that they didn't receive it. And so that helps us to figure out, well, is it because, then we can go back and say, okay, well, is it because they didn't have emergency alerts on their phone? Does it have something to do with the way they were receiving weather information so that we can try and fix that? And so just from just from those 3 events, excuse me, we were able to take away some key points from across those events. And again, this is just one little piece of that data just for time purposes, but I wanted to show you how it's applied. We knew that a higher proportion of respondents received warnings during the evening events, but not in those overnight times. So when people are asleep, right, the early morning events. We know people mostly received those alerts via text messages as they were reported. We know that when we accounted for the difference in the warning reception rate, that most people were still taking protective action at about the same rate, and that the most common protective action people were taking is they were securing their location and making sure that their family was safe. So we can make a lot of we can tell a lot about people's actions just from the social science surveys, and that's another way that data is used. And then that helps us to get to something like this, which are some common misconceptions that people have, so that then we can figure out within our outreach and education, how can we correct these misconceptions? So one of those misconceptions, for instance, is people think that our technologies are so good that they're going to know about a tornado, maybe an hour and a half in advance. And that's just, we're not there yet. We currently have an average warning time of 14 minutes. And so that's not enough time for people to really be leaving their location. That's why we now have started to advise folks in mobile manufactured homes to leave when there's a watch issued and not wait till the warning. Because a lot of people feel like, oh, I'll be able to get in my car and drive home from work or whatever and shelter there. And many times that's not the case. Another misconception is about how the messages will be communicated by like a meteorologist, either on television or on the radio. And they think that the meteorologist is going to tell them where the tornado is coming, like actually name the street. And we know this from several reports from National Weather Service offices, where people are calling the Weather Service office and saying, well, I live on this street, and so is it coming down my street? And some of this has to do with people not having a full idea of the geography around them. We found a lot of time at outreach events, people can't really even spot their county on a local map. And so we have to do a better job of helping people understand that, this is basically what you're going to know within this vicinity of where you're located. And this is where you live. And this is, what you should be watching out for. The meteorologist is not going to be able to tell you necessarily that it's coming down Pine Drive, for instance. There's also misconceptions about how many tornadoes are studied. And so they think we have a much greater database, but actually less than 1% of tornadoes actually get studied. And when you think about the amount of people and equipment that have to get deployed to study them, that makes a lot of sense. And there's also misconceptions about the opening of shelters by the public. And so many think that every shelter is going to be open and they really have to check their emergency management sites, because that's not always true. We found that, if there's not a shelter manager, then they can't open the shelter during the storm. So there's a lot of things that we can find out from this kind of data. So I'll just pause for just a second and just see if I have any questions in the chat box. And Christiana, thank you so much for putting those links in here for us. Okay, well, this is our final section. I just wanted to talk a little bit about what we're calling community weather intelligence, or folks that like to be weather mavens, people that in your community that might really be able to help support what happens with the weather forecasting. And I want to start with a program that the National Weather Service has. It's a volunteer storm spotting program, and they train spotters to report severe weather. They teach them, what kinds of cloud coverage to look for. They teach them how to enter the data so that it gets to the National Weather Service. But storm spotters are extremely important because they are able to help ground truth what we're seeing on the radars back in like the National Weather Service offices and like the emergency management offices. So there is a nationwide program called SKYWARN, and anyone who wants to can be part of this program. It is a free program, and it is generally administered through a National Weather Service office. They do have virtual versions, and they have in-person SKYWARN programs. But I know that every person I've talked to at a weather forecasting office has told me that they find the storm spotters to be extremely important, because a lot of times, like, you'll see this person, taking a picture, they'll send in pictures, and those pictures can be used both on television and by the weather forecasting office, not only to ground truth, but to help other people see, look, there is something on the ground, there's a tornado on the ground, or there's severe weather here in this area. You need to take cover now. So it's really important to the warning decision process, and it does help the Weather Service be able to add statements, maybe upgrading something to a tornado emergency, for instance, if a spotter has some visual evidence of the tornado being on the ground. And we know from other social science studies that the public is more likely to heed a warning if the report has been confirmed. And so that's what the storm spotters do. They actually confirm those reports. So here's some ways that you can become a storm spotter. If you're interested in this and you have any trouble, Christiana and I would be happy to use our weather service contacts and ask them. But generally, SKYWARN is offered in person and online. And you are able to register for this through your local weather forecasting office. And once you become a spotter, you're going to submit reports like either using your phone, or some of them are ham. If you're a ham radio operator, they can show you how to do it that way. There's some online reporting tools, lots of ways that you can do this. But one of the things they stress in the training is to make sure you never put yourself in danger when you're trying to report the weather. So we do have some other SKYWARN resources. Michael Hill, who is at the Jackson Weather Forecasting Office, did a wonderful webinar for us specifically on SKYWARN and storm spotting. The NWS Morristown local office has a virtual SKYWARN class. So if you just Google NWS Morristown SKYWARN, it will take you right to their page, and you can sign up to do the virtual class. So you just do it at your own speed. But we've also seen Jackson, New Orleans, Birmingham, and Mobile offices have all offered these classes. They even have, some of them even have advanced versions of the SKYWARN class. And they usually will put out their schedules for registration on their individual NWS sites. But again, if you want to do this, or you know that you've got folks in your community that want to do it, and for any reason you can't get that, we'll just like contact Michael directly, or contact the folks, at the different offices directly, and ask them when they plan to get those schedules out for the fall. There's usually a fall schedule and a spring schedule. So SKYWARN is another piece of that. It's not a technology, but it's the people portion that helps with the ground truthing. And then finally, I just wanted to show you what Tornado Tales is all about, so that then if you decide that you want to advertise tornado tales in your area, you can do that. So this is that survey that I was talking about, where we can use that social science data that's coming in to help with risk communication messages. And essentially, if you go to this QR code, and I know Christiana will probably put that link also in the chat box, but if you go to this QR code, it will pop the survey up. And it's just a short online survey. And that information does go directly to the National Severe Storms Lab social scientists, behavioral science unit team. And then they collect all the information for a specific event. Now, Christiana and I have been working with them to build contacts in each one of the broadcast viewing areas, because if we know a storm is coming to that area, then we try to send the Tornado Tales survey out to all the broadcast meteorologists in that area, in hopes that then they will also use it when they go online, so that people can find it easily and can self-report. There are some privacy settings, such that when you go in and submit a survey, it's not going to pinpoint your exact local address. It will just pinpoint around an area, just to keep people's address and their identity safe. So all of that has been tested, and we're sure that we're keeping people's private information private. And again, it's just a voluntary. So Christiana and I put this QR code on some bracelets that we hand out at outreach events. We also have some additional resources, such as this extension publication that you see on the far left that we worked on with the Severe Storms Lab. So if you think that this is something you want to use in your outreach or in any of the things that you do, we have these all available online. You can just download it and copy it and take it to your event. If you need something else, like if you're interested in maybe using the little bracelets like what we do, we're happy to help with that. And then before we go, I just wanted to say we also have some extension publications that are based upon questions we've received when we do outreach events. So we have publications just on lightning, just on personal safety, just on building a go kit, all of these things. And we're happy to make those available, most of which are already on our website. And so with that, I know I've been doing a lot of talking. We covered a lot of information, but I did want to leave you with my contact information and Christiana's contact information. We would love to partner with you if severe weather is part of your mission, or if you have need for any resources. Everything we do through Vortex is supposed to be free to the public. So anything that we publish or produce, we can make readily available. to you. If you need to get in contact with a specific scientist at the National Severe Storms Lab, that's something we can also help to facilitate. And then Christiana and I have some very close relationships with folks at our National Weather Service offices in the areas where we work, and they are always a pleasure to work with, and they're always happy to help with events as well. So with that, I will be quiet and see if anybody has any questions. Feel free to take yourself off of mute. Oh gosh, Stephen. Okay, I see Stephen's question. Is there a future use for drones envisioned in weather forecasting? I'm so glad that you asked that question, because one of the resources that I didn't really talk to you about, we did a really cool webinar not long ago. Christiana, if you can find it, let's put that one in there too. There is a project called the Otis Project, and they have a website. It's OTUS. So if you ever want to Google it, but they are actually, this is a group of individuals that have created some small drones. They have a background in drone racing, actually. And so this project is actually flying drones into the center of tornadoes to get a better idea of very accurate wind speed data, much like a hurricane hunter plane is flying through the hurricane to collect that information. The Otis project is doing the same thing with drones. Actually, the Severe Storms Lab has a variety of different drones. I just didn't get into that technology today. But with the Otis project, they will actually go, if they know a storm is coming, they'll set up their van with their data collection in a specific location, and then they will fly the drone. And they actually try to match the speed so that they can get in and sit in the middle of the storm. What I think is so cool about this is they've taken some really amazing video of inside tornadic activity that's helping us to understand better what's happening inside that vortex. And then I think the other thing that's really cool is that they're working with NIST, which is a federal agency, to try and calibrate the instrumentation on the drones so that then they know that they're getting accurate wind speed and direction information, because that's really hard to account for when you're actually flying an object into the storm. So I think there's a lot of utility for future things happening with drones. When we talked to them and hosted this, they had been filming for a Netflix special on the Otis project. So I think this is really a project to watch. If you're interested in just the drone instrumentation that's being used currently at the Severe Storms Lab, I do have some pictures of those from my last visit up there, and I do have some good contacts for the folks that are using that drone technology. Okay, let's see, Xavier, a data repository. Not that I know of for each one of these specifically, but if there is specific data that you need, we can take that same question, Xavier, and we can send it to our project team up at the Severe Storms Lab, because typically what we've noticed is they have like these teams of scientists that work on very specific, physical science or social science things. And so if we know what the data need is, we can just ask that inquiry and see which ones of those data sets are publicly available. But a lot of what they do, because it's funded by the federal government, a lot of what they do does have to be publicly available. That's a great question. So Christiana and I will chat that one down. And if you want to leave us with your email contact, we can let you know. I don't personally know of one that would have all those different sources, but I don't want to misspeak. So we'll find out for you. Thank you for that question. Any other questions we could maybe answer for you today about the technologies that we discussed? Or maybe there is another topic specifically on storm tech. And if you have an interest in that, we would love to hear that as well, because we often will ask guest speakers to come on and really talk in depth about a specific topic. And that's why you see all those other webinars that Christian has put in the chat box, is because it helps to receive that information from the source. Okay, well, I will be happy to stick on for a few more minutes to see if folks have questions. But I also would just like to thank you for your interest in today's webinar. You can follow us on social media, as Christiana just put into the link that goes to all of our social media accounts. And also, we have other topics. We can send those out to you if you have an interest. But please let us know if there's other topics of interest to you, or if maybe you're an expert in a particular severe weather topic and you think that that's something that other people might be interested in. We're happy to meet with you and see if there's ways that we can get that information out to a broader audience. So thank you so much for joining us today, and we look forward to seeing you in a future training.